Hello everyone, welcome back. In this example, we are asked to find the inverse of the function f of x, which is defined by the rational equation or rational function 2x plus 1 in the numerator divided by 3 minus x in the denominator. And so we have a short little multi-step process that allows us to find algebraically the inverse equation for a function. The first step we always do in this process is rewrite the function in terms of y and x. And so all that means is we want to for now abandon this function notation and remember that all f of x really is our output or placeholder for y. So in terms of x and y or y and x, our function is y is equal to 2x plus 1 divided by the quantity 3 minus x. And so what this equation y equals 2x plus 1 over 3 minus x is really telling us is the rule that is true for our function that connects the inputs or the x values to the outputs or our y values. And our next step is going to be translating this relationship or this rule into the rule for our inverse functions. And to help us kind of establish that rule, we have to remember that for a function and its inverse, the inputs and the outputs switch positions or switch roles. Every output becomes an input. Every input becomes an output. And then what that means for us algebraically and symbolically is that every y is an output, that becomes an input. So every y becomes an x. And every x that was an input now becomes an output or a y. And so our original y was representing the output of our function. Our new y's down here after the swap in our second step are really representing not the output of our original function, but the output of our inverse function. And so now our final step, basically our final step, we have one little one after this, is to solve for our new y, solve for y in this equation after we swap the roles of x and y. So one of the big issues that is making it difficult for us to solve for y at the moment is we have a y in the numerator as well as a y down in the denominator. So we're going to clear our fractions by multiplying both sides by this denominator, which is that quantity 3 minus y. So we have to multiply the left-hand side of our equation by 3 minus y. That's how we obtain x times 3 minus y. Then we have to also multiply the right-hand side of our equation by 3 minus y. But when we multiply the right-hand side by 3 minus y, it's going to cancel that factor of 3 minus y out from the denominator, leaving us just that numerator 2y plus 1. So that helps us get rid of that issue of having y's in both the numerator and the denominator. But now we have y's on both sides of our equation. So we've gotten rid of one problem but introduced a new problem. The nice thing is this newer problem is a bit easier to work with. So what we want to do from here is expand everything and then try to start combining like terms. So on the left-hand side, that's the only place where we can really expand anything. We just distribute that factor of x throughout our quantity in parentheses. That'll give us 3 times x minus x times y. And now we want to start grouping or collecting like terms. So what I mean by that is let's get everything with a y on one side of our equation, maybe the right-hand side, and everything else on the other side. We're trying to group all the terms of the y together because our goal now is to solve for this new y. So it doesn't matter if you move all the y's to the left-hand side or to the right-hand side. I'm going to move them to the right-hand side just so everything has a positive sign instead of a couple negative signs. You'll get the same answer either way. It might look a little different, but you're basically just multiplying by -1 in both the numerator and the denominator. All right. So if we want all the y's stuff on one side, we need to get this +1 that is on the right-hand side over to the left-hand side. So we'll have to subtract 1 from each side to help us do that. We already had this 2y on the right-hand side. We need to get rid of this xy on the left-hand side or a negative xy on the left-hand side. And we do that by adding xy to each side. And so now this whole point of collecting everything with a single factor of y on one side of our equation is now we can factor that common factor of y out of all those pieces on that side of our equation. So if I factor a y out of 2y plus x, I'm going to be left with 2 plus x, right? We can always redistribute or expand that quantity to double check our work. Y times 2 gives us 2y, y times x gives us xy. It's looking good. And now we're just about finished with this step. To finish solving for our new y, we just have to divide away by 2 plus x. So I'm going to kind of flip both sides of our equation here just because we always like to have y on the left-hand side for some reason. But when we solve for y, we should end up with 3x minus 1 in the numerator divided by 2 plus x. So this equation really is the inverse of our original function. And our final step is just to remember that this new y is not representing f of x anymore. It's representing f inverse of x. And that switch happened when we swapped the roles of x and y early on. So our inverse function has the equation f inverse of x is equal to 3x minus 1 over 2 plus x. This function's a bit more difficult to work with than some of our other inverse functions we found. That's why I wanted to go through all this algebra together. But we could still, if we had the time and the desire to do it, check all those inverse properties of this function. Meaning if we were to graph our original function and the inverse function on the same set of axes, the graphs will just be reflections of each other over that line y equals x. And also, if we were to compose these functions in either order, plug f of x into f inverse of x, or f inverse of x into f of x, it might take a while to do the algebra and simplify everything, but once that dust clears, everything would cancel out and we would get just x, which is what we always see when we compose a function with its inverse.